Fn equal to mod, that is same as this function only. Fn equal to mod n. This is exactly same as this function because n is already positive. So this function is not different. It's the same function. Okay. Aro kichu try karo. What is this function? 1 goes to 1, 2 goes to 2, 3 goes to 3, 4 goes to 4. You try to modify here. এখানে দেখো না, এখানে চেঞ্জ করা যায়। How we will change? Right? How we can change this? Try to modify something here. The diagram that we change for you will get a different function. Here 1 goes to 1, 2 goes to 2. Change that. Better change for change for how I can change? Forget about these things. Just concentrate on these two. This is a function from the set 1 2 2 1 2. So how I can change? Diagram ta change probably. 1 goes to 2. Here 1 goes to 1. So just change that. 1 goes to 2. Okay. So you get a different function. 1 goes to 2 or 2 goes to 1. So this is another function. And everything else goes to itself. F of 1 is 2, f of 2 is 1, and everything else is fixed. Okay, Fn equal to n for all n. Okay, so then we get a different function. So this is also 1 1 1. Okay, so this function, how will you define f from n to n? Defined by f of n equal to f of 1 equal to 2, f of 2 equal to 1, and f of n equal to n for all n greater than or equal to 2. Okay, so this is the definition. So in the first day also I told you it's not necessary that a function will be defined by a single expression. Okay, a function may not be defined by a single expression because there are three expression lagse. F1 is 2, f2 is 1, and fn is n whenever n is greater than or equal to 3. Okay, so this is also 1 1 1 2 function. Bijection. This is also bijection. So how many bijections we can create from n to n? But create another one. Arekta create karo. Create another bijection. 1 goes to 3. F1 is 3. Then F3 is 1, and everything else remains same. Fn equal to n for otherwise. Okay, you can also define this way. F1 is 3, F3 is 1, and otherwise Fn is always n. Okay, this is another function. So how many we can define? Infinitely many. Okay, just change this. F1 goes to say 2020. F2020 is 1. Everything else is same. Okay. So these are actually placeholders. You can take anything here, any natural number, and then the corresponding one you place that natural number here and assign it to 1. Okay. So then lots of functions we can define. Okay. So here I have just interchanged two elements. Tinta element here korte pare. Okay. Say f1 goes to 2, f2 goes to 3. Okay, and f3 goes to 1. Okay, this was we will do. So actually we are taking a permutation of 1, 2 and 3. Okay, we are taking permutation of first 3 elements, and all other elements are kept fixed. Okay, that is the way. Tinta element I will permutation, and everything else remains same. Okay, so lots of functions you can define. Right. So you can take something like f1 is 2, f2 is 3, f3 is 4, f4 is 1. Okay, so this is the permutation of 4 elements. and everything else remains same. Fn equal to n for all n greater than or equal to 5. Okay. So there is no shortage of functions. There are lots of functions. Onek functions define kora jaybe. Okay. So many one functions, bijections you can define from n to n. Lots of projections. Okay. So if you write something like fn equal to n square, in that case it is not onto, because there are many numbers which are not perfect squares. So under this function, say the number 5, it will not have any preimage, because n square equal to 5, it will imply that n is plus minus root 5. Okay, so that is not allowed. So this function cannot be onto. Okay, it cannot be a bijection. Okay. Next, let us define composition of functions. Composition of functions. Okay. So how will we define composition of functions? Right. So let f from x to y and g be a function from y to z. So we will combine these two functions to get a new function. Then, so we can combine it this way: x, starting from x we go to y, starting from y we go to z. Okay, so we can define the function GOF. Okay, GOF can be defined. Then the composite GOF of or the composition of f and g. Composition of f and g is the function. GOF. So this will be a function from where to where. So the order is this. First f is applied. Okay. So order is from right to left. Okay. This way it is applied, right to left. So first f is applied and then g is applied. Okay. So f works on this domain x. Okay. And ultimately g goes to that codomain. So GOF goes from x to z. Okay. So is the function GOF from x to z defined as GOF of x. Okay. So what happens to a particular element of x under this function? So that particular element goes to g of fx. Okay. Because fx is an element of y. X is an element of capital X. So fx is an element of capital Y. Okay. X belongs to capital X. Fx belongs to capital Y. But g is a function from y to z. So g of fx will belong to z. Okay. So that is the definition. First we find the image of x under f. Okay. And then we find out the image of fx under g. Okay. That is the system.
Sir, assignment. Assignment submission.
Oh, assignment को तो कल के अपलोड करो इसलिए. हाँ, डेट माने कब सबमिट करता है?
Submission date.
हाँ, आर क्वेश्चन पेपर दो इसलिए. तो एग्जाम सेल तक ही देखो. एग्जाम सेल तक ही दो और क्वेश्चन पेपर हमने तो माने एक मास आगे बढ़े. देखो तो. Okay. So GOF from x to z we can define this way. So in this situation can you define FOG? FOG টা define করতে পারবে না. FOG here cannot be defined. because g goes from x y to z, okay, but f is from x to y, okay. So it can be defined if this z is a subset of this capital X, okay. In that case we can say something like f of g, okay. So it's not necessary that, so function composition is not commutative, okay. GOF and FOG, they are different, okay. Duita will be different functions. If if one of them is defined, it may happen that the other is undefined, okay. Say for if it is something like this f is a function from say 1 to the set 5 6, okay, and g is a function from the set 5 6 to the set 7 8, okay. In that case GOF is defined, okay. GOF, that is defined, but FOG is not defined because see g goes from this to 7 8, okay. So after we apply g, we cannot apply f because we can apply f only in this domain 1 2, okay. So FOG, GOF, they are very much different, okay. So function composition is not commutative, okay. Okay, so we will note that down. So let us write here, note that function composition is not commutative. Okay, so FOG is not same as GOF. In fact, so that is FOG. This function is not equal to this function. In fact, it may happen that one of them cannot be defined even if the other is defined, okay? Even if the other is defined, okay. So it may happen that one of them cannot be defined even if the other is defined, okay. So for example, f from say the set 1 to the set f is a function from this to this, and g is a function from 3 4 to 5 6, okay. In this case GOF is defined, okay. GOF, this is a function from 1 to f goes from here to here, and then g goes from here to here, okay. So it goes from this to 5 6, okay. So when we define composition, this and this, they have to be the same, okay. The same. Okay. So in this case, the GOF, this should be, so at least this should be, this one should be a subset of this, at least, okay. Right? Otherwise we cannot say. So GOF is a function from 1 to 5 6. Right. But FOG cannot be defined. Okay. Cannot be defined here. Okay. So we cannot define FOG here. Yeah. So okay. However, from x to y and g from y to z. Okay. If z is a subset of x, okay, if this z, this is the g of z, that is the image range of z, actually, range of g. If the range of g is a subset, okay, then we can define. It's not necessary that the whole codomain should be a subset. Okay, the range could be a subset. Yeah. So if the range of g is a subset of x, okay, means whatever elements are there, image elements are there under g. If those elements lie inside x, in that case we can define. Okay. With this, then we can define FOG. Okay. FOG, which will be this from y to what? G will be from y to z, and this will be from x to y. Okay. So this will be from, sorry, what did I say? G O F. Yeah. This may be from another one. So in this case, it is from y to y. Okay. Like this. Right. In general, if f is a function from x to say y and g is a function from w to z, okay, where so f from x to y, no? So fx lies in y, right? If I want to apply g again, those fx should lie inside w. Okay. So where y is a subset of w, okay, or say the range of y, the range of f is a subset of w, okay, and the range of g, okay, is a subset of x. Okay. So if the range of f is a subset of w, okay, and the range of g is a subset of x, okay, then we can define both FOG and GOF. Okay. FOG and GOF. Okay. So this is the condition in general. If f is a function from x to y and g is a function from w to z, where range of f is a subset of w, okay, and range of g is a subset of z. Okay. Sorry, range of g is a subset of x. Okay. Then we can define both FOG and GOF. Right. So this can be done. So in that case, what will be GOF? In this case, what will be GOF? It will be a GOF will be a function from x. From x it will go to y. From y it will go to z. Okay, so it will be a function from x to z. Right, and FOG will be a function from. So it will start from w, okay, and will go to y. W to z they go. Then that particular subset range is a subset of x. So from x it will go to y. Okay. So FOG will be a function from w to y. Okay. So that is okay. So this is the condition under which we can define composite functions. Composition of functions. Okay, so let us try some examples. So this also you have done at theory. Exercise, let f from R to R and g from R to R. G is a function from R to R. Be defined by fx equal to say x squared or say x cubed for all x inside R, and g of x equal to 3x plus 2, okay, for all x inside R. So you find out what is FOG and GOF. Okay. Find these two, FOG and GOF. So here everything is same. This domain, codomain, everything is same. So both will be defined. No problem. Okay. So try to find out what is FOG and what is GOF. Try. What is FOG? FOG will be a function from this R to R, from here to here. So FOG will be a function from R to R, defined by is defined as FOG of x is equal to f of gx. Yes. So f of first you have to apply this inner one. So what is gx? Gx plus 3x plus 2. So this is 3x plus 2, and then you apply f. And f of x is x cubed. So f of this will be 3x plus 2. This is acting like x now. This quantity is acting like x. Okay. So FOG of x is 3x plus 2 whole cube. Okay. Then GOF from R to R. This is defined as what? GOF of x. This will be G of fx. Okay. G of fx. So this is G of what is fx? Fx is x cubed. X cubed. And then apply G. So what is that? 3x cubed plus 2. So x cube is acting like x, right? So you see, in general they are different. FOG and GOF, they are different. Okay. They may be equal at some points, okay, but as functions they are different. Right? 3x cube plus 2, 3x plus 2 whole cube. So what difference? Okay, let us try another one. F is a function from exercise is f is a function from R to 0 infinity, and G is a function from 0 infinity to R, 0 infinity to R, defined by f of x equal to x squared and g of x equal to root x. Okay. So you try to find what is GOF and FOG. So find FOG and GOF. Okay. So from where to where FOG will be defined, from where to where GOF is defined. Okay, try that. FOG will be a function from this 0 infinity to 0 infinity. Open closed interval. Yeah. This 0 infinity, you read it as closed interval 0 to infinity. Okay. What does it represent? It represents all real numbers which are greater than or equal to 0. All non-negative real numbers. Okay. This is the real. So FOG will be a function from is a function from 0 infinity to from here to here to 0 infinity. So how it is defined? FOG of x will be f of gx. Gx is already root x. F of root x means root x square. So that is x. Okay. So FOG of x is x here. And what is GOF of x? GOF of x here is, so this is a function from GOF is a function from R to R. Okay. You see the domain, is it? Domain starts from R. Okay, and domain of the first from right to left. Okay, domain of the first to codomain of the second. Okay, that way you have to do. Domain of the first to codomain of the second. Okay. So GOF goes from R to R. So GOF is a function from this. Your GOF of x is G of fx. So this is G of fx. Fx minus x square, and x square is a positive one. So G of this is root over of x square. Okay. So what is root over of x square? Square root of x square is what? It is the positive square root of x square. What is that answer? X. But this is incorrect. Why it is incorrect? This is not correct. Huh? The correct answer is what? Mod x. Okay. Root over of x square is mod x. It may happen that the x that I chose here was something like -1. It also will. No? Because the domain here is R, so I could have chosen something like -1. So in that case, what is GOF of -1? It will be G of f of -1. F of -1 is what? F of -1 is 1. Okay. So this is root over of 1. Okay. So this is the positive square root of 1. So this is 1. So this is not same as x. No? This is not same as x. The x that I chose was, what was x? X was -1. Okay. So this is not x actually, this is mod x. So always remember, root over of x square, this is not equal to x. This is actually equal to mod x. Modulus of x. So here FOG and GOF are actually different. Okay. It may seem, if you write it as x, you means the conclusion will be incorrect. If I write it as x, it will mean that these two functions, FOG and GOF, are equal. Okay. But actually they are not equal. Actually they are not equal. Okay. FOG, GOF, they are not equal. Right. So GOF is not 1 1. Okay. This is a FOG is FOG. This is 1 1 function. FOG is a 1 1 function. Right. FOG of x, it goes to x only. Okay. But this is not 1 1 because GOF of -1 is same as GOF of 1. Okay. So this is not 1 1. So your answer is actually mod x. Lower of x square is mod x. Here. So be very careful. Okay. Acha, you try another one. If f comma g from R to R defined by f comma g from R to R defined by are defined by f of x equal to x cube plus 2. Okay, and g of x is equal to cube root of x. Okay, the third root. Third root of x. Find FOG and GOF. Find FOG and GOF. Is FOG equal to GOF? That is what you have to find. Find FOG and GOF. Is FOG equal to GOF? Try this. Not equal. What is FOG here? So here what is FOG of x? So both are functions from R2 because everything is equal here. So FOG of x here will be f of g of x, which is f of cube root of x. Cube root of x. So this is cube root of x whole cube plus 2. So cube root of x whole cube is x plus 2. This thing is x plus 2. And GOF of x, this will be g of fx, and this is equal to g of x cube plus 2. G of x cube plus 2. So what is the here? So this is the cube root of x cube plus 2. Cube root of x cube plus 2. So they are not equal. Cube root of x cube. If it is something like x plus 2 whole cube, in that case it would have been equal. X plus 2 equal. Here it is not equal. This is x plus 2. So in general they are unequal. For example, you can take one value like x equal to 1. Okay, if you take x equal to 1, this is what? FOG of 1. FOG of 1 is 3 and GOF of 1 is cube root of 3. So they are unequal. If two functions are different even at one single point, they are unequal. Okay.
Sir, cube root of x cube.
Cube root of
X cube.
Cube root of x cube. This is x only. This is not mod x. Okay. This is just x. Whenever this we take even nth root. If we take nth root, which is where n is even, in that case mod will come. Okay. Otherwise, mod will not come. Because -1 cube is always -1. Okay. The problem happens when the power here is even. If it is even power. If it is odd power, there is no problem. Okay. So of course, this is the real cube root. In your trigonometry, you will see cube root. Actually, whenever we find out the cube root of some quantity, there are three. Just like square roots, there are two square roots of any real number. Any non-negative real number. If we consider negative real number, when we go to this complex analysis, okay, or say so in that case, this your square roots of -1 plus minus I. Okay, when we go to the complex number system, okay, in that case we can define this square roots as this. Okay, so in your trigonometry, you have seen first unit started from roots only. The De Moivre's. Okay, so there you will get something like this: cube root of 1. Okay. Cube root of 1. The real cube root is only 1. Okay, but together with that, there are two imaginary or complex cube roots. Okay, these are omega and omega square. Okay, means if we solve this equation x cube equal to 1, any polynomial equation of nth degree will have exactly n roots. Okay, they may be equal, they may be unequal, they may be real, they may be complex. Okay, so that is the fundamental theorem of algebra. Okay, so we have to include complex numbers, otherwise a particular equation may not have exactly this 3 roots. Okay, we have to go to the complex number system. Only then that will be true. Otherwise, the number of real roots we can discuss. So here x cube equal to 1, it will have only one real root. Okay, but the other 2 roots will be imaginary, complex. Okay, so the real root will come from this part, the complex root will come from this part. So x equal to minus 1 plus minus root over quadratic equation formula. B square minus 4 is 1 minus 4. So it's minus 1 plus minus I root 3 by 2. Okay, so which one is omega, which one is omega square? Okay, so there is no hard and fast rule that you should take this class as omega plus minus. If one is omega, another is omega square. These are just symbols. So if one of them is omega, square that, you will get the other omega square. Okay, right? So when we talk of real roots, real cube root of x cube is only x. Okay. So similarly for fourth root also there are 4 here. Suppose fourth root of 1. Okay. So what are the fourth roots of 1? Fourth roots of 1. Okay. So 1 minus 1 I minus n. Okay. So there are 4 fourth roots. Okay. Similarly, nth roots of unity. Okay. So there are n such roots. Nth roots of unity. Okay. So here we are dealing with only real numbers. Okay. So this real analysis part we will deal with only real numbers. So that is why for us cube root of x cube will be just taken as x. Okay. Right. Okay, now let us see some theorems. So if suppose f is 1 1, g is 1 1, what happens? Can I conclude something about g over f o g? Okay. If f is onto, g is onto, then can I conclude? Okay, those type of things. Okay, so this we will write it as a theorem. Let f be a function from x to y and g be a function from y to z, then number one is if f and g are 1 1, f and g are 1 1, then g o f is 1 1. Okay. If both the functions are 1 1, their composition is 1 1. Number 2, if f and g are onto, then g o f is onto. Right? So from these two it will follow that if f and g are bijections, then GOF is a bijection. So let us quickly prove this. Ekdam simple proof, just it requires basic understanding of 1 1 on 2 concept. Okay, 1 1 and 1 2. So if f and g are 1 1, then GOF is 1 1. Okay. So how will you prove it? Number 1. So I have to prove that GOF is 1 1. That means distinct elements of this X will go to distinct elements in Z. Okay, that is the right. So let So we will take GOF is a function from x to z. So we will take two elements from the domain, that x1, x2 belongs to x, such that so if their images are equal, I have to show that the elements have to be equal. So GOF of right. So I'll show it in two ways. This is one way. So if these two are equal, ultimately I have to conclude that x1 and x2 are equal. Okay. So just apply the definition. G of f of x1 is equal to g of f of x1. Okay. So from here what conclusion I can do? F of x1 equal to f of x2. Why? Because this g is 1 1. G is given to be 1. Okay. Since g is 1 1. Okay. So that is why I can apply this. G is a 1 1 function. So f of x1 will be equal to f of x2. Next, I can apply the fact that f is 1 1. Okay. So from here I can write x1 is equal to since f is 1 1. Okay. F is 1 1. Okay. So I can conclude. So these two are arbitrary elements. So therefore GOF is 1 1. Okay. So if f and g are 1 1, then GOF is also 1 1. Okay. So this is one way of proving. Another way is we have two forms of the definition. Okay. Distinct elements will go to distinct images. Another way we can try. Another way. Let x1, x2 belong to. So we take two elements from the domain which are unequal. Okay. Such that x1 is not equal to x2. Okay. Then f of x1 is not equal to f of x2. Okay. Because f is 1 1. Since f is 1 1. Okay. We take two unequal elements and so we can conclude that fx1 is not equal to fx2 because f is 1 1. Now these two are unequal elements of y. Okay. Also g from y to z is 1 1. Okay. 1 1. And these two are elements of g. Okay. This is 1 1 and fx1, fx2, they are actually elements of this y. Okay. So therefore, these two are unequal elements of y. So g is 1 1. So g of f of x1, this is not equal to g of f of x2. Okay. So from here I can conclude that g of f of x1 is not equal to g of f of. Okay. So if we start from two unequal elements of x, the GOF image will be unequal. Okay. So distinct elements in x will have distinct elements in z under the function GOF. Okay. So that is another way of proving 1 1. Okay. Both are correct. You can do it in any way. Right. So let us try this one to part. Okay, but please note that the other way it may not be true. If GOF is 1 1, it may happen that one of G of f may not be 1 1. Okay, we will see some examples. Okay, let us try number 2. So I have to show that GOF from x to z is on to show that GOF from x to z is on. So that means what? Every element in the codomain has a pre-image. Okay, so I'll take an element here in the codomain z. Okay. So let z small z, okay, let small z belongs to capital Z be any element. Okay, be any element. Okay. So if I take an element from, so I have two functions একটা হলো গিয়ে x from f from x to y, another is g from y to z. Okay. And both of them are on. It is given that both of them are on. Okay. So if I take an element from here z, then what I will get? Huh?
F of z equal to 1.
Huh? No. From here. From z, if I take an element, g from y to z is onto. That means every element here will have a pre-image in y. Okay, under the function g. Okay. So for z inside capital Z, we will get a y inside capital Y such that g of y is equal to z. Okay, that is what we will get. So let z belongs to this z be any element. So then since g from y to z is onto, okay, y to z is onto, so there exists y inside capital Y, okay, small y inside capital Y such that g of y is equal to z. Okay, z. Okay, g of y is equal to z. Okay. So we have got an element y inside capital Y. Okay, which satisfies this.